Graphical analysis. Okay, let's go ahead and assign direction. Let's make up positive. We're going to call that plus y. Let's say we have someone that throws a ball. Oh, there's my nice hand there. Throws a ball upward. And when they throw this ball upward, it leaves their hand with an initial velocity of 10 meters per second. That's a positive 10 meters per second because the ball is going upward, and we assign upward as positive. Now the ball goes up a total distance of 5 meters, and we'll call that delta y. And at that point, when the ball reaches its highest point, we're going to call that velocity 0 meters per second. That's when the ball reaches highest point. And that ball actually has to stop for a moment so it can change direction and then come back down. So at the highest point, when a ball is thrown upward in the vertical position, that velocity is 0 meters per second. Now, what we don't have in this example is the time it takes for the ball to go up and go down, and we're going to need that so we can graph this. So what I also don't have written down here is what is the acceleration. And when a ball is near Earth's surface or under the influence of gravity, it also experiences an acceleration. So let's address the acceleration. The acceleration has a special value, small g. That stands for the acceleration due to gravity, and that has a value of negative 9.8 meters per second squared. This is the acceleration that an object experiences in the absence of air near Earth's surface. The negative responds to the fact that there is a force of gravity pulling towards the center of the Earth. Now, what is the time that this ball experiences when it's thrown up and then comes back down? Well, 1/2 of the time can be found by using this formula here. I want to put a little subscript of 1/2 because that will tell us the time for the ball to go up. And if we could find the time for the ball to go up to its highest position, that will be equal to the time it takes to come back down. So my final speed in this case is going to be when it's at its highest position, so it'll be a speed of 0. My initial velocity is a positive 10 meters per second plus. My acceleration in this case is g, or negative 9.8. You know what, let's say that's approximately, see if I can fit this in here, 10. Negative 10 meters per second squared. So let's plug in a negative 10 meters per second squared. And then the unknown here is 1/2 of the time for the total trip while the ball is in the air. So what I would like to do is subtract 10 meters per second on both sides. So I get negative 10 meters per second is equal to a negative 10 meters per second squared multiplied by my unknown, 1/2 of the time. I'm going to go ahead and divide both sides by negative 10 to solve for t to the 1/2, and I get 1/2 of the time is equal to 1 second. So that's the time for the ball to go up to its highest point, and then it will take another second for the ball to come down. So the total time of flight is going to be 2 seconds. Alrighty, let's graph this example in a position versus time graph. So we're going to have a y-axis and a time axis. This is my time. This is my position, y, in meters. This is my time in seconds. This is my position versus time graph. Now, for the time, we know that the ball was in the air for a total of 2 seconds. So I'm going to have mark this. This would be a time of 0 seconds, 1 second, 2 seconds. At the top of its flight, the ball was up at 5 meters, so this right here will be 5. I'll do different colors so we can see the 5 hiding in there. And so at 1 second, the ball had reached its highest point. So let's do that. That's right there. At 0 time, the ball didn't have any height above the hand, so that was here. I'm going to use red. Let's see if we can see that better. Red, red. And at 2 seconds, the ball was back down in the hand. It turns out the speed that the ball is released from the hand at 0 seconds is the same speed that the ball is going when it reaches the hand at 2 seconds, just in opposite directions. Now, we end up having a curve that shows what the ball is doing as it goes up and goes down into the hand. Now, as you recall, I believe we had talked about acceleration. It turns out, real quick, let me go back here. If you're talking about the slope of this graph, the slope of this graph, or any graph, is your change in your vertical divided by the change in your horizontal. So in this case, my vertical is my change in my y on my graph, and my horizontal is my change in my time. In this case, this could also be said this is my change in position, change in my y position over change in time, or displacement over time. This, folks, is known as velocity. Now, this velocity has a curve, or this graph is curved. So when you have a curved graph, that means your velocity is changing. And when your velocity is changing, this is a way of saying that there is an acceleration happening. And the question is, what type of acceleration is happening? So if you recall, we did a little chart, or we may have talked about this in class last week, but we can have a plus A, we can have a plus A, we can have a minus A, we can have a minus A. So we're going to have 2 plus A's or 2 minus A's. It's determined on what's your direction and what is happening to your speed. Let's do a little chart here. Let me choose blue. Now, if your direction is positive and your velocity is increasing, we say you'll have a plus A. If your direction is negative and your velocity is decreasing, you have a plus A. If your direction is positive and your velocity is decreasing, you have a minus A. And if your direction is negative and your velocity is increasing, you have a minus A. So when we look back at our green curve, or our graph here, let's see if we can figure out what type of A is happening between, say, 0 and 1 second. So when you look at the curve here, you can see that we're moving upwards, or what we call positive direction. So we're either going to look at this one or this one. And then the question is, when the ball is released from your hand and reaches its highest point, is the ball speeding up or slowing down? And the answer is the ball is slowing down because it comes to a stop when it reaches its highest point. So we're dealing with a negative A for 0 to 1 seconds. For what's happening from 1 to 2 seconds? Well, from 1 to 2 seconds, we have a direction going down. So let's use a different color here. So, or negative direction. So it's this one or this one. And then when the ball is coming towards your hand, is the ball speeding up or slowing down? And the answer is the ball is speeding up. So again, we have a negative A from 1 to 2 seconds. All right, now let's see if we can graph the same situation in a velocity versus time graph. And in our velocity versus time graph, our horizontal axis will be our time. our vertical axis will be our velocity. This will be our plus velocity up here. This will be our minus velocity down here. Remember, plus velocity means you're going in a positive direction. Minus velocity means you're going in a negative direction. Now, if you recall, we were dealing with a total time of 2 seconds. So this is 2. This is in seconds. This is 1 second. And this is 0 seconds over here, 0. Remember, your velocity is in meters per second. Okay, now at 0 seconds, that's when the ball is just released from the person's hand. The ball is going in a positive direction, and it's going at, say, I believe we determined that to be 10 meters per second. At 1 second, the ball had reached its highest point. At that point, the ball is going at 0 meters per second, and 0 meters per second is right along the horizontal axis. Maybe I'm going to use green here. So the green was the 10. And then at 1 second, the ball is going 0 meters per second. And then it changes direction. It starts going in a negative direction. And at 2 seconds, that's when the ball is going all 10 meters per second as well, but in the opposite direction. So that's going to be right here. This is going to represent negative 10 meters per second. And this happens at 2 seconds. So our velocity versus time graph looks like this. It looks very different than our position versus time graph. As a matter of fact, when you connect the points, what you end up getting, and I'm going to try and freehand this here, is a straight line. Now the slope of this line is going to be the change in your rise or your vertical over your change in your run or your horizontal. That's going to be, so let's write here slope. That's going to be the change in your velocity over the change in your time. This, folks, this is called acceleration. Now in this case we have a straight line. It's not a curve. So a straight line means that we have a constant slope or a constant acceleration. And if our slope is our acceleration, I guess my question to you is this a positive slope or a negative slope? Hopefully you're able to see that this is a negative slope everywhere. It's the same everywhere and it's negative everywhere. Hence we have a negative acceleration. Recall in our position versus time graph, we showed that we had a negative acceleration. Now lastly, what I wanted to talk to you about with this graph is how can you find displacement with this graph? You can actually find displacement with this graph with not finding the slope, but finding the area between the horizontal axis or the time axis and the line on your graph. So let's say I wanted to find out what is the displacement at, we'll call this at 1.5 seconds. So the object has traveled 1.5 seconds. Based on the graph, what's the displacement? So we're going to find the area from where we started of that right there. And so the area, let's write this here, the area for the first part, we have a triangle, and we're going to add that to the triangle beneath the horizontal axis. So the triangle above the horizontal axis, which is the area for a triangle, I believe is 1/2 base times height, is going to be the 1/2, the base is 1 second, the height is 10, and we're going to add that to the area underneath the time axis, which is going to be 1/2. The time in this case, the time I'm interested in is only from the 1 second to the 1.5 second, and the time or the difference between those two is 1/2 second or 0.5. And then this height here is going to be the speed at this point. And so by using the kinematics equations, I figured out that this speed is going to be -5. And so when I add those, first of course I get these two answers, and then I add them, I will end up getting a positive 3.75 meters. This is going to be my displacement, otherwise referred to as my delta y, or 3.75 meters above my hand. So as a recap here, on a velocity versus time graph, we can find the acceleration. If we have a straight line, it's a constant acceleration. But we can also find displacement with the velocity versus time graph by finding the area. All right, lastly, I want to talk to you about an acceleration versus time graph. My horizontal axis is my time in seconds. My vertical axis is my acceleration in meters per second squared. 0, plus, minus. So based on the same situation of a ball being released from someone's hand or my hand, and it goes up and comes down, what does this look like on acceleration versus time graph? Well, as you recall, we already said that we had a constant acceleration and that it was a negative acceleration. So when you look at our graph here, negative acceleration is below the t-axis. There's my little negative there. And as time goes on, the acceleration stays the same. As a matter of fact, that acceleration is that special g value. It's approximately, well, first of all, it's negative 9.8 meters per second squared. And we're going to round that to make life easier. It's about a negative 10. So that's the constant acceleration we're talking about. As time goes on, it's going to stay that value. So how would you represent that as on this graph as time goes on? You would represent this as a straight horizontal line as time goes on. This represents my negative 9.8. Now what if right here represents 1 second? And I said, oh, what was your, my question to you is, what was your change in velocity in 1 second based on this graph? Well, what you can do is find the area of this here, and this area, which is going to be length times width, or 1 second, times the width, which is negative 10 meters per second squared, is going to give me negative 10. That area gives me the, see if I can fit it in here, the change in velocity. So that gives me the change in velocity. So let me rewrite that. I'm going to do that a little bit better here because I left off my unit. That's negative 10 meters per second. We always want to have our unit. So the area of the acceleration versus time graph will give us our change in velocity. All right, that's it for now for graphical analysis.